We're going to be talking about representations of solutions. So just to review really quick your intermolecular forces, there's dispersion forces, which are typically between nonpolar molecules. Although any molecule can have it, it is the most important in those nonpolar molecules because nonpolar ones do not have the other intermolecular forces. The larger the molecule, the more electrons it has, the more polarizable. More polarizable means it's going to form more London dispersion forces. And when you're representing this, we usually use dotted lines for all of the intermolecular forces, but it doesn't really matter where exactly you put them in dispersion forces because it could happen kind of anywhere randomly as the electrons move. Dipole-dipole, on the other hand, when you're drawing, you need to make sure that you're doing that dotted line between the positive end of one molecule and the negative end of a different molecule. So in this case, the polar acetone molecule, the oxygen here is slightly negative, and the hydrogen on the chloroform is slightly positive. And so it creates those dipoles in each of the molecules, and then they can attract each other. So just make sure that you're lining them up negative to positive. Hydrogen bonds, of course, hydrogen bonding is fun. So, and I saw, this is kind of an issue that I saw from the section 1, so 3.1, but you need to make sure that when you're bonding this, like in ethanol here, the oxygen is attached to a hydrogen with a covalent bond, and then that's attached to a carbon, etc. But that hydrogen can then form a hydrogen bond with the oxygen on a water molecule, for example. The FON that we're talking about refers to which atoms the hydrogen can covalently bond to and also form a hydrogen bond with something else. So for example, this hydrogen here can form a hydrogen bond with something else because it is attached to oxygen. Or maybe you have HF. This hydrogen, because it has a covalent bond to fluorine, that hydrogen can form a hydrogen bond with another molecule. So the FON is referring to what atom the hydrogen can covalently bind to and also form a hydrogen bond with something else. The last type, of course, is ion dipole, and that's just between a polar molecule and an ion. And you just, again, need to make sure that the charges are lining up properly. So if you have a positively charged ion, you want to line up the negative end of a polar molecule. But if you have a negatively charged ion, you want to line up the positive side of the polar molecule. Okay, let's talk about miscible versus immiscible. Miscible is just a fancy word for mixable. So miscible things can dissolve in each other. If it's immiscible, it is not mixable. It will form layers. So the kind of the mantra that we use is like dissolves like. But this is not an explanation. It's just like a memory tool. So what that means is that nonpolar substances are likely to dissolve in nonpolar solvents, whereas polar substances are likely to dissolve in polar solvents. And that's because of their intermolecular forces. So nonpolar things will pretty much only form dispersion forces. It's going to dissolve with other nonpolar things because they also have dispersion forces. If you try to mix a nonpolar substance with a polar substance, essentially what happens is the polar things stick together really strongly using those dipole-dipole interactions. If you then have a nonpolar substance come in, let me try to use a different color that shows up. The nonpolar substance come in. In order for it to dissolve, it would have to form intermolecular forces with the polar substance. But that would involve breaking those dipole-dipole forces, and the nonpolar substances cannot break those interactions typically because they cannot form strong enough interactions. They can only form dispersion forces. So that's why you wind up typically with two layers. And Very frequently, the nonpolar substance will be less dense, so it will float on top, but not always. The less dense substance will form a layer on top of the more dense substance. So that's kind of where you get like dissolves like. They're more similar. The intermolecular forces, the more likely it is that they're going to be able to form intermolecular forces with each other to form that mixture, to form the solution. So here's a better illustration of what I was talking about on the previous slide. When you're forming a solution, there are interactions or intermolecular forces between the solvent particles. There are intermolecular forces between the solute particles. And in order for a solution to form, you have to break at least some of those interactions and form new ones between the solvent and the solute. So, based on the strengths of those interactions, that will determine whether or not this solute can dissolve in the solvent. So if the solvent-solvent interactions or the solute-solute interactions are too strong, then it cannot form solvent-solute interactions. But as long as these ones are stronger, then your substance will dissolve. And so that's kind of how solutions are able to form. Now, just to make sure that you're okay with drawing these concentrated solution, there's typically large amounts of solute in a given volume, whereas a dilute, you have a relatively small amount of solute in a given volume. And just make sure that you're able to draw the difference there between the particles in a concentrated versus a dilute solution. Okay, so let's practice drawing those hydrogen bonds in ethanol. So ethanol, this is one molecule of ethanol. It has 2 carbons, an oxygen, and then a bunch of hydrogens. But this hydrogen on the end here is the only one that can form hydrogen bonds. These hydrogens on the other side cannot form hydrogen bonds because they're attached to carbon. This hydrogen on the end is attached to oxygen, so that means that that hydrogen can form a hydrogen bond with something else. It's going to be attracted to the oxygen on a different ethanol molecule because the oxygen is slightly negative and the hydrogen is slightly positive. So there's your hydrogen bond. You could have also done the reverse and used this hydrogen, which is attached to an oxygen, and hydrogen bond there. Okay, you cannot form a hydrogen bond between 2 hydrogens. You cannot use the hydrogens that are attached to the oxygens for hydrogen bonding. Okay, so if we want to draw a particle representation of KCl dissolving in water, the 2 ions K and Cl will separate because it's a soluble salt. So potassium and chlorine will be separate. And when it dissolves in water, it's going to form ion dipole interactions, which means that the positive charge on the potassium is going to interact with the negative side of the water molecule, which is the oxygen side. So you want to make sure that the partial negative from the oxygen is oriented towards the positive side, or the positive ion, like this. And the hydrogen on the other side. Whereas for the chlorine, you want exactly the opposite. The negative from the oxygen should be away, and the partial positive from the hydrogen should be toward the chlorine. The partial positive, partial negative. And so that's how the KCl is going to dissolve with the particle diagram like this.